Agnes, and we are looking at Chapter 3, Section 3. It's titled Solving Problems with Systems. As a student, I'm looking for you to be able to solve word problems using systems of equations. And this is not something to intimidate you. You're going to see by the end of this lesson that using systems helps to eliminate a lot of that guessing and checking that you have had to use up until now. So it's a more systematic approach. Get it? All right, so let's get started. Our first example asks us to find two numbers whose sum is 23 and whose difference is negative 81. Now I get it. Some of you can just do that in your head, and that is awesome. You are incredibly gifted and blessed by the Lord. Now, some of us have different blessings and gifts from the Lord, and so we have to write this all down. A good way to do this is first try to represent what you're looking for as a variable. So we're going to let x be the first number, and we'll let y be the second number. And we need to write this down because if we don't write down what each variable means, it's easy for us to forget. Then we'll create a plan. In this planning, you're actually setting up your equations here. We know that x plus y is 23 and x minus y is negative 81. These two equations can be solved using, of course you could graph them and you could use substitution, but elimination is the best method here because your y variables are additive inverses. You'll have 2x equals negative 58. The y's cancel out, and that leaves us with x again being negative 29 if you divide each side by 2. Now, the question wanted us to answer what are the two numbers. So now that we know our first number, we need to find our second number by plugging in our known value into our equation and solving. So y is 52. That would be the second number. We have to give our answer in regard to the problem, which means you're going to use a sentence to respond. The numbers are negative 29 and 52. And it's really important to check your answers, and really it's awesome to be able to check, to know how to check, because then you have no excuse for ever getting it wrong. When you plug in x and y into these two equations and you use your calculator to check, negative 29 plus 52 is 23, and that is our initial equation, what we wanted it to equal. And negative 29 minus 52 is in fact a negative 81. So we mathematically checked it by substituting back into our original equations, and we have answered our question in the context of the problem. So that's all for example 1. Let's move on to example 2. All right, this problem is an investing problem. Mr. Perry has invested a total of $10,000 into 2 stocks. AmeriCorp returned 8%, meaning he earned 8% on that investment, while Bancorp returned 10%, meaning what he put in, he earned 10% more. How much did he invest in each stock if his total return last year was $850? All right, so first thing, we should be able to represent what we're looking for. What are we looking for? How much did he invest in each stock? So X, we'll let it be the amount invested in the first one, which is AmeriCorp, and Y is the amount invested in Bangkor. And now we need to devise a plan, and this is where we're going to have to use a formula and a table. There is a formula used to find the amount gained on an investment. It is the principal times the rate times the time. So we're going to use all of those values to determine how much is gained, how much is earned or returned from those two different stocks. So the principal is Ms. Ruiz. No, but really in this context, the principal is the amount invested initially. And that is what we don't know. But we have said that for AmeriCorp it's X and for Bangkor it's Y. The rate of return for AmeriCorp is 8%, which is 0.08, and 0.10 for Bangkor. The time, well, it was only 1 year for each of them. So to find the amount gained, you would multiply that row. So it would be 0.08x and 0.10x. That is how much was gained. 8% of the amount invested at AmeriCorp and 10% of the amount invested at Bangkor. And I just am seeing here that should be a Y, 10Y. My mistake. I'm so sorry. I am an imperfect, sinful human being. Okay, but let's move on and solve the equation. X plus Y, the amount invested in Bangkor and the amount invested in AmeriCorp, should give you $10,000. That is how much he invested. And the amount gained are those two separate gains added together. And it should give us $850. All right, now this, I'm going to use substitution. I'm going to solve for Y by just subtracting X and plug that expression into my second equation. When you plug that in, it looks like this. Negative X plus 10,000 in place of where the Y was. Distribute the 0.10 to each term in the parentheses, and then combine like terms. I passed the 1,000 to the other side by subtraction, and I combined the 0.08x and the 0.1x. Dividing by negative 0.02 gives us that x is 7,500. And very quickly I can plug that into the equation where my y is isolated, because that's what I need to find. And that gives us 2,050, which together is in fact 10,000. But we're going to now answer this in the context of the problem. He invested 7,500 in AmeriCorp and 2,500 in Bangkor. And plugging in those two values into both equations in your system, it will in fact make them true. And you can check that right now. Pause the video and make sure that the results do generate the equations that we started with. Example 3. This is a distance problem. We're working with two buses and they are 412 miles apart and they're heading towards each other. So I want you to visualize this, two buses moving towards each other. One is traveling 3 miles per hour slower than the other, and they meet in 4 hours. What is the average speed of each bus? That last statement, what is the average speed of each bus? That's what we're trying to find. So R sub S will be the rate of the slow bus, and R sub F will be the rate of the fast bus. Our plan, like I said, it's a distance scenario. Rate times time gives you distance. R times T gives you distance or equals distance. So with these, we're going to be able to create some equations. The rate of the slow bus is r sub s, and for the fast, it was r sub f. The time for each is the same, and the distance is the product of those. All right, so now let's create our two equations. R, the rate of the slow bus, is 3 miles slower than the rate of the fast bus. And you guys have been doing a lot of bell ringer problems like that, so you probably already kind of visualized that. And then the distance will be 412 when added together. So the distance that the slow bus went and the fast bus went together or added should give you 412. Now, substituting in, we'll be able to write this as an equation in terms of the fast bus, distributing, and then combining like terms, dividing each side by 8, we find that the rate of the fast bus is 53 miles an hour, which means 53 minus 3, the slow bus was going 50 miles an hour. Now we need to write that using our words. The slow bus traveled at 50 miles per hour and the fast bus at 53 miles per hour. And this could be checked by plugging in the values that we found into our original equations and making sure that the result is true. So for the first, it is in fact 50, and when you take 4 times 50 and 4 times 53, that is 412. Fantastic. All right, here is our final example. We're working again with a distance problem, and this one's kind of fascinating because it has to do with water as well. So, during rainy season, a boat can travel 60 kilometers downstream in the same amount of time that it takes to travel 36 kilometers upstream. If the boat can travel 16 kilometers per hour in still water, meaning like on a lake where the water's not moving, what is the average speed of the current? All right, so what are we looking for? We are looking for the rate of the current. We'll let that be the variable c. And we're also wanting to determine the time of each trip. We don't know how long that length of time that the boat was going either up or down exactly was. So again, we create a table that we can put our values into, delineating between downstream and upstream. Downstream, you are able to go 16 kilometers an hour plus the speed that the current helps you to go faster, because if you're going downstream, the current is pushing you, it's helping you to go faster. Upstream, you're having to fight against the current, which is going to slow you down. So it's 16 minus however fast your current is. The time that we go up and downstream is the same, but the distances are different. Downstream, in that time we went 60, and upstream we went 36. All right, so now we have to remember that rate times time is what gives you distance. So we set this up. Rate times time for downstream is 60, and rate times time for upstream is 36. Distributing the t to both parts, you'll see that we can actually just immediately carry out elimination of that second term, the CT terms. So you'll have 32t equals 96, and dividing each side by t means our time is 3. 3 hours is what we're working with. Now that we know t, you can plug that in to one of the initial equations to find the rate of the current. Distribute 3, or I'm sorry, it'd be faster to divide each side by 3. And then solve for c, that will be 4. So the rate of the current is 4 kilometers per hour. And that's pretty fast. That's a lot of movement of water all at one time. And you could check this by plugging in the time and the current, those speeds and time, into those initial equations and making sure that they equal what they were designed to equal, which is 60. That's true for the first, and 36. All right, that is all. If you had any questions, make sure that you wrote those down in the margins and we will discuss them together. Thank you. Goodbye.